Anytime you're studying mathematics, it's very important to understand the notation being used to describe the problem. In statistics, we're generally concerned with drawing a conclusion about something called an estimand, which is some unobserved quantity in our problem. Now, estimands can be observed, or I should say observable, or not observable. And we'll try to be consistent regarding how we denote them, the notation that we use for them. So let's talk about some of the notation that we're going to use in Bayesian statistics. The letter Y is going to denote a vector of observed data. Most of the time this is going to be a vector of n values, but it could be a realization of a single random variable. So for example, this could be a vector containing the weights of a sample of words. The letter theta is generally going to be used to describe a vector of unobservable model parameters. So in most contexts, there's going to be several parameters in our study, but there may only be one. So some examples are we may have the mean and variance of a normal data distribution, or perhaps we have only the rate parameter of a Poisson distribution. The letter Y tilde is going to denote a vector of observable estimates or observable quantities of interest. So you can note that the link here between Y and Y tilde. So the tilde lets us know that this is something that we could observe given enough time. So for example, this might be the future selling price of my home if I chose to sell it. I may not be able to observe it now, but I could make a prediction based on a model and then at some point in the future see how close my prediction was to what I predicted, or to how close my prediction was to how much my home actually sold for. The last letter we'll talk about right now is the letter X, which we're generally going to reserve for covariate or explanatory variable information. This is additional information that we use in our problem and in our model, but we're not going to model as random. We're going to assume that this is something that we know ahead of time, and we're just going to assume it's a known fixed value. Xi would refer to the ith value of the explanatory variable, or in other words, the value of the explanatory variable for the ith observation. Xij would refer to the jth explanatory variable, and the I part of it would represent that information for the ith observation. Let's talk about a key assumption in Bayesian statistics. So one of the key assumptions in Bayesian statistics is that the observed data are known as exchangeable. What that practically means is that our joint probability distribution is invariant to permutations of the indices. In other words, it doesn't actually matter what order we observe the data in, the probability distribution is going to be the same. How do we know if a set of observations are exchangeable? Well, really, it's better to ask if they're not exchangeable. So observations are not exchangeable if the value of the index actually gives us some information about the data itself. So for example, if we had a time series, the order of the data might be very important. So the good news is that any set of data can be made exchangeable as long as we include enough covariate or explanatory variable information in the problem. So for example, for a time series, we would include the actual time the data was observed as one of the explanatory variables, and that would allow us to treat the observations as exchangeable. With the exchangeability assumption, one of the things we commonly do in Bayesian statistics is that conditional on the model parameters and possibly on some covariates, we typically treat our observed data as being from the same distribution and identically distributed. So in other words, we treat our observed data as IID, conditional on enough information. And if our data are IID, then they have to be exchangeable. And because of that assumption that we make about the data being IID, conditional on the data, it's pretty easy to make the assumption that our data are in fact exchangeable so that we can perform Bayesian inference.